ISP's acting terrible. Okay, so we had the equation y prime equals x squared plus y over x. We did an Euler method. Let's solve the equation. Now there's something weird about this. My solution doesn't seem to be a solution, but it seems to work very well. And I haven't resolved this, so there's something you can play around with. Okay, it's a very simple process to solve it. Made a couple of arithmetic mistakes. You can see where I erased things. Need a minus here. Okay, the integrating factor is, of course, I've rearranged the equation here, and now it's in the form of a non-homogeneous first order linear equation. So we find an integrating factor. And that integrating factor is e to the negative integral of, e to the integral of negative 1 over x, which is e to the negative natural log of x, which is just 1 over x. It's the exponential function, and I don't know who's talking. Unfortunately, I didn't record what I did here. That's me, but I'm going to go over it kind of quickly because I'm trying to. And this should reinforce it for everybody that's watching. If you have the Michaels. Okay. I need to close that. And he'll shut up now. Okay. A file that's been opening for about 30 minutes finally opened. Should have opened in 3 seconds. Okay, so we got our integrating factor. We multiply through by the integrating factor, and we get this. Now I'm going to let you check that. You know how to do these. Then this expression is the differential of y over x. At least, no, it's actually the derivative of y over x. But anyhow, this side is the differential of y over x, which is 1 over x y prime minus 1 over x squared times y. You take the derivative of this with respect to x, and you get that. So this equals x, so y over x, and I'm being a little careless with notation. I don't want to mess with that, but y over x is the integral of x dx. Integral of x dx is x squared over 2. Y over x equals that. And of course, we have the integration constant. So y is x cubed over 3 plus cx. Okay. Now, the initial point was 1, 1. So y has to equal 1 when x equals 1. If x equals 1, this is 1/2. This is 1. So cx had better be 1/2. So we have 1/2 plus 1/2 equals 1. X is equal to 1. So c has to be 1/2. So this would be our solution, and I don't think I ever wrote it down, but c equals 1/2, so that you have, let me see that, yeah, y equals x cubed over 3 plus x over 2. Well, all that's great, but now if I plug this back in up here, y prime is going to be x squared over 2 plus 1/2. Okay, well, we get an x squared over 2. We get a 1/2. So that y over x has to equal 1/2. And when y equals 1 and x equals 1, that works out, except it doesn't quite, because there's a constant that comes in here. Work it out yourself and you'll see. So it doesn't seem to work. However, in Excel, I did the approximation with an h equals 0.01, and I got an equation pretty much y equals, well, it said 0.5 x cubed, and then it had something, a small number times x squared that I'm going to eliminate. It didn't make much difference, but then it was plus 0.515x. Well, that's real close to x cubed over 3. Make that look like a decimal instead of 0. That's pretty close. Well, that's x cubed over 2. Why did I say 3? It's x cubed over 2. I wrote a 3. I must have wanted to write another 3. And x over 2, which would be 0.5x. Now, the approximation isn't exact. So this is a fit to the approximation, but this is so close to this that I have to believe this solution, even though I don't believe it, but I plug it into my head. Who knows what might have happened. Everything agreed except that the y over x gives me a 1/2. And that 1/2 isn't, well, actually it gives me a 1/2 and y prime gives me a 1/2. Okay, so it works. Okay, well, anyhow, so amidst all that confusion, I went back to Excel. And this thing doesn't want to share that. This thing wants to share this. Actually, it shares what I asked it to share. So I thought that the thing I wanted was highlighted, but yeah, it's getting late and I'm a little aggravated with the ISP. So here it is. Okay, yeah, I clicked on where I thought it was, but not where it was. Okay, so what I have over here is, in the first place, I have the graph. I don't know if you're going to be able to read this because I don't know what kind of resolution you're going to get. I think this is the graph, but let's see. Nope, that's not it. There it is. Okay, so here's the graph. And what you've got here is 0.05x cubed, that's your 1/2 x cubed, and then a minus 0.0149 x squared, and then a 0.515x, and then minus 0.00005. Okay, again, the curve here is the curve I got from the approximation. Okay, so the values you see are here, actually here. These are the values we got from the approximation. Okay, these are the solutions we get from the x cubed over 3 plus 1/2 x. So we see 1.02, don't know if you can read it well, and 1.020105, 01505. The discrepancy being 0.00015. Well, you don't expect much discrepancy on the first step, but you notice that the discrepancies between this and this, and by that I only mean that this is this minus this. Now, let me remind you, this came from Euler's method, from the approximation, and this came from the solution function. So we still have 2 zeros here, okay? In other words, the discrepancy between the actual and the Euler approximation is this small, 0.003, 3 parts in 1,000, okay? We don't get down to 1 part in 100 until we get to a y value of 2.276 by the approximation, 2.286 from the actual function. Those are very close, only off by 0.1, which is less than 0.5%. The errors keep building, but they don't build very fast. By the time we're at x coordinate 1.76, and we're looking at x values between 1 and 2, by the time we're out here, the discrepancy is now up to 0.02. And that's out of the actual value 3.65. So that's up to about 2/3%, a little less than 2/3%. Okay. And it goes on. And by the time we get out to x equals 2, the discrepancy is only 0.03 out of 5. Okay. And that's still well less than 1%. It's about 0.6%. Well, just that process of me looking at the solution here and doing it carelessly and making a couple of silly errors with numbers. I came out with the right solution. Okay. And I didn't have much trouble coming out with the right solution. I didn't believe the solution because I plugged it in here in my head and something was wrong. But I think it works. You can plug it in and see. But thinking that this was wrong and not really liking that CX there much, I believed, okay, I must have screwed something up. Then I did the trendline fit, and I chose a degree 3 polynomial. First, I chose a degree 4 polynomial, and I still got pretty much this. The x to the fourth term had a coefficient of like 100,000th or something like that, and these terms were the same. So the idea that you can work with the software and get through some stupid things you do, and everybody's going to do stupid things. Not as many as I do, but everybody will do some stupid things. By checking that, I confirmed this solution to my satisfaction, even though I still hadn't gotten my head right about the substitution. I was getting a term that didn't seem to belong there. If I'd have written it out carefully, I wouldn't have had that problem. Lesson 2, write things out carefully. So there it is. And you have this impressive agreement at this level. Now, we do notice that, and I think I've got it up here if I can get up far enough. Yeah. Yeah, I'm not sure that's right. So let's go down here again. Okay, at 2, I got 5.06 from this approximation. And at x equals 0.5, I got 3.9. Well, something isn't gelling. Nevertheless, you get an idea of how you can look at these things, how they work. And as I said before, I was convinced that the thing had to be concave up. I made some kind of mistake in Excel, which made it look like it had to be like the approximations were getting lower and lower. Whereas on a concave up graph, they got to get higher and higher because you're always underestimating the slope, because the slope as you project forward is always greater than it is at the point. Okay, well, think about those things. It's good stuff. Let's see if I can get the mouse to behave.